let's go through, work through an example, and really this is, I think, the kind of thing I'll try to do as much of this as I possibly can in terms of working out example problems, because I think that's really where online learning probably excels in some way. Let's take a look at this particular problem. Let me pull it down a little more. An example. This is, again, something from really that you had before the spring break, extended spring break. But it's a good review process for us to pick up some things that we skipped over or we would have gotten to no matter what. In any event, here we have an 18 gauge wire. This is the kind that's pretty typical in table lamps like you might have in your living room or maybe at your desk. And at 18 gauge, it's kind of interesting. The wire is actually made by mechanical engineers, and they're the ones that control this language about 10 gauge and 18 gauge and 20 gauge. But they all get translated over into a diameter. So you usually have to look these up. But if you work enough in it, then I guess you remember. I never remember what the diameter of 18 gauge wire is. So either look it up on the internet or you pull up a mechanical engineering book of the ones who actually make wire. Yeah. But in any event, 18 gauge wire has a nominal diameter of 1.02 millimeters. And this particular wire carries a current of 1.67 amperes to a 200 watt light bulb, so a fairly high wattage light bulb. And it's made out of copper, and they tell you the density of free electrons is 8.5 times 10 to the 28th per cubic meter for copper that the wire is made from. And they want you to find the current density in the wire, the drift velocity of the electrons making up the current, the electric field in the wire, the potential difference between the two ends of the wire if the wire is 50 meters long, and ultimately the resistance of the wire. I drew a little picture here from the data that you're given. It's obviously not drawn to scale. The length of this wire, since you're given the diameter, I assume it's a cylindrical shaped wire. There's a current going down it. But the diameter is the 1.02 millimeters, and it's pretty long, so I guess you were running it out to your barn or something. I don't know why it would be 50 meters, but in any event, that was the statement of the problem: 50 meters of length. There's some preliminaries that you really need to do, and that is from the wire diameter. You need to calculate the cross-sectional area, and the area is just the area of this end piece here that the current is assumed to be uniformly distributed across. Uh, uh, the area of that circle is pi r squared, and the radius is half a diameter, and so 1.02 times 10 to the minus 3 meters. Millimeter is 10 to the minus 3 meters. And I take half of that to get the radius and then square it. When I did it in my calculator just a few minutes ago, I got 8.17 times 10 to the minus 7th square meters. And now I'm in a position where I can actually do the current density. If you remember from before spring break, the current density is represented by J. And for uniformly distributed currents over that entire, uniformly distributed across that entire area, the current density is the total current flowing through the area A divided by the area. So here, that A is area, as is this one up here. And now that I'm given that the current is 1.67 amps, so the A here is a unit ampere, and we just calculated the cross-sectional area as the 8.17 times 10 to the minus 7th meters squared. And we get the answer to part B, which is to find the current density, a little over 2 times 10 to the 6th amperes per square meter. That's pretty typical for sort of normal household currents and what the current density is in wire. Current density, we then in part B, we're asked to find the drift velocity. And so go back if you look through your notes before spring break. Current density is the charge, the magnitude of the charge in this case. Really, I'm looking at the magnitude of the current density. Is the magnitude of the charge on electrons, since it's the electrons that are the free particles. The number density of free electrons. I've been represented in that in class notes as n sub f, but your book just uses a little n. And then v sub d is the velocity that these charge-carrying electrons making up the current have. And we can solve that for the drift velocity, v sub d. We just found the current density. The magnitude of the charge on the electron is 1 times 10 to the minus 19th coulombs. And the number density that was given to us in the statement of the problem above is 8.5 times 10 to the 28 electrons per cubic meter, but it's just a number per cubic meter. And if you look at that, numerically it comes out to be 1.5 times 10 to the minus 4. We need to get the units though on it. And it's ampere per meter squared, and then I divide by coulombs, and this meter cubed rolls over on top. And I did one conversion. 1 ampere is 1 coulomb per second, and so my amperes will cancel out, and then my coulombs will cancel. I've got a meter squared, which will cancel 2 of the powers there, and I'm left with meters per second. And so the drift velocity is 1.5 times 10 to the minus 4th meters per second. If I turn that into millimeters, you see that it's not very many millimeters that it's moving. In fact, if I looked at it for 10 seconds, it would only move little over 1.5 millimeters. Very slow velocity. So typically these electrons that are making up the current, the charges that are moving in wires, is a very low number. And what I always draw the analogy to is it's kind of like a fog bank. If you've ever been to San Francisco and you can go down by the pier and watch the fog roll in the evening. The fog bank moves in very, very slowly. And that's kind of the way these electrons in the current move through the solid, through the copper, at a very, very slow rate. But as we've seen, that can produce a very high current density and even a nominal 1.67 amperes. Next part, you're asked to find the electric field, and you have to remember this relationship. We'd gotten this, I think, before break, that the current density is related to a constant here, sigma, which is the conductivity of the material, in this case copper, because it's a copper wire, times the electric field in the wire. And you can solve this for the electric field, since I already know the current density, calculated that in part A. Divided by sigma. But remember, the 1 over of the conductivity is equal to the resistivity. And this would be as a material property. And so we have to go look up. In general, you'll have to either be given or look up in tables the resistivity for copper. And I looked it up online, actually, in the source I pulled up from online for the resistivity of copper at sort of room temperature is little over 1.7 times 10 to the minus 8 ohms times meters. And that 1 over sigma is the resistivity, and so the electric field is equal to the resistivity times the current density. And then plugging in our value for copper times the value of the current density that we found in part A. Then multiplying that out, I get 0.035. One of the meters cancels, so on top I'll get an ohm meter, an amp times an ohm. But remember, V equals IR, so 1 volt is current in amps, resistance in ohms, so an amp times an ohm is a volt. And so the electric field, in this case 0.035 volts per meter, that exists in the wire that causes the electrons to move at this very slow rate of the drift velocity, that produces really a pretty reasonable current of almost, well, a little under 2, 1.67 amperes. Part D was find the electric field, and in magnitude anyway, the electric field is the change in potential over the change in length. Okay? And for us, the length of the wire is L, and I can solve that for delta V. The voltage difference across the distance delta x is just E times L, and sometimes that's not a bad formula to remember to begin with. But we're given those things. We've actually found 0.035 volts per meter was the value for the electric field, and the length we were given for the wire was 50 meters, and so that turns into 1.75 volts as the total voltage drop from one end of the 50 meter copper wire to the other end. Then ask for what's the resistance, and there's several ways to get the resistance of that wire. One is I can just use Ohm's law. The voltage difference is equal to the current times the resistance. I know the voltage difference. I got that in D, and I know the current that was given originally. And so the delta V is the 1.75 divided by the current that's going through it, 167. And when I divide that out, I get a little over 1 ohm. So the resistance of that 50 meters of copper wire, 18 gauge copper wire, is about 1.05 ohms. Now, at this stage, there's lots of ways we can get the resistance, and one formula that you had both in lab and also in class was that the resistance was equal to the resistivity times the length of the wire divided by the cross-sectional area. And at this stage, we know all of those things. We've looked up the resistivity for copper, 1.72 times 10 to the minus 8 ohm meters. We know the length was 50 meters, and the cross-sectional area, we calculated that the very first thing for the wire, which is this 8.17 times 10 to the minus 7 meters squared. And when you do all that calculation, I get 1.05 ohms. So oftentimes on these problems, there's multiple ways to get it. Either one of these, you wouldn't have to do both ways, but either one works fine on this one. Although you might notice this one maybe is a little bit quicker because you kind of already calculated everything here to get the 1.05 ohms.